Hello students, welcome to the class Mathematics. I am B. Srinivasa Rao. Now let us start our class. Students, we learned the concept of congruent figures in our earlier classes. What are congruent figures? The figures that have the same shape and same size are called congruent figures. Suppose, let us take these two figures. Now, we have to decide whether these two figures are congruent or not. So, how can we decide? Now, I am placing this figure on this figure. What happens? We can observe that the boundaries of one figure coincides with the boundaries of the second figure, which means they are the exact figures. Such figures are called congruent figures. For the congruence of triangles, we have also learned SSS congruence, SAS congruence, ASA congruence and RHS congruence. Okay children, now in this class we are going to discuss the very useful concept, that is similar figures. What are similar figures? The figures that have the same shape but need not have the same size are called similar figures. Now let us try to understand the concept of similar figures. For that, let us take these two circles. It is very clear that these two circles have the same size. Now can you say that these two circles have the same shape? How to decide? How to know? For that, we do one thing. Let us place the smaller circle on the bigger circle. Okay, can they coincide with each other? No, because their sizes are different. Now we do one thing. Let us enlarge the smaller circle. What happens? After some enlargement, the boundary of the smaller circle coincides with the boundary of the bigger circle. Like that, if the boundary of the smaller figure coincides with the boundary of the bigger figure, we can say that those two figures are similar. That's why here we can say that any two circles are similar figures. My dear children, now let us take these two rectangles. So here also these two belong to same kind of quadrilaterals. Okay, now let us see whether these two rectangles are similar figures or not. Here also, as before, let us place the smaller rectangle on the bigger rectangle. Can you say that their boundaries coincide? No, because they are of different sizes. Now we do one thing. Let us enlarge the smaller rectangle. Now what happens? In any stage of enlargement, the boundaries of the smaller rectangle coincide with the boundaries of the bigger one? No, not at all. So here, though they belong to the same kind of quadrilaterals, these two rectangles are not similar figures. That's why here we can say that any two rectangles need not be similar. And in the same way, if you take any two line segments, we can say that they are always similar. Now we can see that one. Here we are enlarging the smaller line segment. So after enlargement, it coincides with longer one. So here we can say that any two line segments are similar figures. So like that, students, we can understand that if the figures have the same shape, then we can call those figures similar figures. But students, you tell me, is it always possible for us to decide whether the given figures are similar or not by the observation or by enlarging the smaller figure? Not always possible. That's why we need a formal definition for similar figures. That's why there is a definition for similar polygons. Let us see what it is. So here two polygons are said to be similar if their corresponding angles are equal, and the second condition, the lengths of their corresponding sides are proportional. If these two conditions are satisfied, we can say that the given polygons are similar figures. Students, now let us try to understand the two conditions of similar polygons. For that, let us take the square ABCD of a side 2 units and the rectangle PQRS of the measures 3 units and 4 units. Now, let us take the first condition, that is corresponding angles are equal. We know that each and every angle of a square and a rectangle is 90 degrees. That's why here we can say that the 4 angles of the square are equal to 4 angles of the rectangle. That's why first condition, that is corresponding angles are equal, is satisfied. Now let us take the second condition, that is the lengths of the corresponding sides are proportional. What does it mean? First here, let us take the ratio between the sides. For example, AB and PQ, let us take. The ratio between AB and PQ is 2 by 3. And in the same way, ratio between BC and QR. What is the ratio between BC and QR? That is 2 by 4. Are they equal? No. So here, corresponding sides are not in proportion. If all the 4 ratios between the corresponding sides are equal, we can say that the lengths of the corresponding sides are proportional. But here, first condition, corresponding angles are equal, is satisfied, but second condition has failed. So, can you say that square and a rectangle are similar figures? No, we can't say, because only one condition is satisfied. That's why they are not similar figures. Now let us take a square of side 2 units and a rhombus of side 2 units. Now let us verify their similarity. For that, first let us take the first condition, corresponding angles are equal. In a square, each angle is 90 degrees. Can you say that each angle in a rhombus is right angle? No. That's why here the first condition itself has failed. So here we can say that a square and a rhombus are not similar. Now let us take any two different squares. One is of side 2 units, the other is of side 5 units. Now here we can observe that these two squares are always similar, because in these two squares each angle is 90 degrees. That's why first condition, the corresponding angles are equal, is satisfied. And if you take the second condition, that is the ratio between the corresponding sides, that is 2 by 5, 2 by 5, 2 by 5 and 2 by 5. Here all these ratios are equal. That's why the lengths of the corresponding sides are proportional. As these two conditions are satisfied, we can say that any two squares are similar. Students, you remember one thing. If you take any two regular polygons of same number of sides, they are always similar. It means any two equilateral triangles are similar, and in the same way any two squares are similar, and any two regular pentagons are similar, etc. So, my dear students, from this discussion, we can say that for the similarity of polygons, only one of the two conditions is not sufficient. Both the conditions have to be satisfied. But in the case of similarity of polygons of 3 sides, that is the similarity of triangles, if any one of the conditions is satisfied, then automatically the other condition is also satisfied. That's why we can give the definition for similar triangles like this. Two triangles are said to be similar if the first condition, corresponding angles are equal, or here we need not use and. The second condition, the lengths of the corresponding sides are proportional. That's why, for the verification of the similarity of two triangles, if one of the conditions is satisfied, we can declare that those two triangles are similar. Basic proportionality theorem. It is also called Thales theorem. The statement is, if a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, then the other two sides are divided in the same ratio. Now, let us picturize this statement. For this, let us take the triangle ABC. Now, let us draw the line parallel to the side BC to intersect the sides AB and AC in two distinct points D and E respectively. Now, let us write the given information in the statement. That is, in triangle ABC, DE is parallel to BC, which intersects the sides AB and AC at D and E respectively. RTP required to prove, that is, AD by DB is equal to AE by EC. Students, sometimes the information given in the statement may not be sufficient for us to prove the conclusion in the statement. In those cases, we need to add some more details to the rough sketch, which we call construction. For that, let us join the points B, E and C, D, and also draw DM perpendicular to AC and EN perpendicular to AB. Now, let us see the proof. For this, first let us consider the triangles ADE and BDE. Students, if you observe, these two triangles stand on the line segments AD and DB, which are on the side AB. Now, let us take the ratio between the areas of these two triangles ADE and BDE, that is, half into AD into EN by half into DB into EN. Students, here we can observe one thing. The heights of these two triangles are equal because their bases lie on the same line and the vertices of these two triangles opposite to their bases are the same. After cancelling the equal factors, we will get the ratio AD by BD. Again, after considering the triangles ADE and CDE, which stand on the side AC, if you find the ratio between the areas of these two triangles, you will get AE by EC after the simplification. In these two ratios, if area of triangle BDE and area of triangle CDE are equal, we can say that AD by BD is equal to AE by EC. But if you observe, the triangle BDE and the triangle CDE are on the same base DE and between the same parallels BC and DE. But we know that the triangles on the same base and between the same parallel lines are equal in area. So, we can say that area of triangle BDE and area of triangle CDE are equal. Now, from these three relations, we can conclude that AD by DB is equal to AE by EC. Now let us see the converse of the basic proportionality theorem. The statement is, if a line divides two sides of a triangle in the same ratio, then the line is parallel to third side. Here also let us picturize this statement. Here ABC is the triangle and D is the line which divides the sides AB and AC in the same ratio, that is, AD by DB is equal to AE by EC. Now let us write given. In triangle ABC, D is the line such that AD by DB is equal to AE by EC. Next, RTP, that is, DE is parallel to BC, that we have to prove. Now let us see the proof. First of all, let us assume that DE is not parallel to BC. Students, If DE is not parallel to BC, definitely there must exist a line through the point D such that it is parallel to BC. So let us take that parallel line as DF. Now students, as DF is parallel to BC, we can say that AD by DB is equal to AF by FC by the basic proportionality theorem. Now it is given that AD by DB is equal to AE by EC. Now from these two relations we can say that AE by EC is equal to AF by FC. Now if you add 1 both sides of this equation and simplify, you will get AC by EC is equal to AC by FC. Then it will give the condition that EC is equal to FC. But it is possible only when the points C and F coincide with each other. That's why our assumption that DE is not parallel to BC is wrong. So we can conclude that the line DE is parallel to BC. Students, now let us do some problems in exercise 8.1. Here let us see the first one. In triangle PQR, ST is a line such that PS by SQ is equal to PT by TR and angle PST means this angle is equal to angle PRQ. Then prove that triangle PQR is an isosceles triangle. Students, to prove this result, first let us consider the given conditions. Of those, let us take the first condition. What is that? In triangle PQR, it is given that PS by SQ is equal to PT by TR. So, from this we can say that ST is dividing these two sides PQ and PR in the same ratio. But by the converse of basic proportionality theorem, that is, by the converse of Thales theorem, we can say that if any line divides two sides of the triangle in the same ratio, then that line is parallel to third side. So here ST is dividing PQ and PR in the same ratio. We can say that ST is parallel to QR. ST is parallel to QR. So let us write the same. By converse of Thales theorem, we can say that ST is parallel to QR. For these two lines, PQ is the transversal. As these two lines are parallel, we can say that corresponding angles are equal. So, angle PST is equal to angle PQR. Let us write the same. And for these two parallel lines, PQ is the transversal. PQ is the transversal. Therefore, angle PST is equal to angle PQR, since they are corresponding angles. They are corresponding angles. But there is another condition given. What is that? Angle PST is equal to angle PRQ. Now, from these two conditions, what can we tell? As these two angles are equal to angle PST, which is the same, we can say that these two angles are equal. That is, angle PQR is equal to angle PRQ. So, these two are the angles in the triangle PQR. But we know that if in any triangle, if two angles are equal, we can say that that triangle is an isosceles triangle. Therefore, we can say that triangle PQR is isosceles. Like that, we can prove this result. Students, now let us see the third problem in exercise 8.1. In the given figure, DE is parallel to AC and DF is parallel to AE. Prove that BF by FE is equal to BE by EC. Here, first let us take the condition DE is parallel to AC. DE is parallel to AC in the triangle ABC. So let us write that first. In triangle ABC, what is the first condition? DE is parallel to AC. But we know that by the Thales theorem, if any line is parallel to one of the sides of a triangle, it divides other two sides in the same ratio. By that, as DE is parallel to AC in the triangle ABC, we can say that BD by BA is equal to BE by EC. Let us write the same. By basic proportionality theorem, as D is parallel to AC, we can say that BD by DA is equal to BE by EC. Let it be first condition. Now let us take the second condition. What is that? The second condition is DF is parallel to AE. So what are they? DF is parallel to AE. This situation is in the triangle ABE. That's why in triangle ABE, we can say that by the given condition DF is parallel to AE. Again, by the basic proportionality theorem, here also we can say that as DF is parallel to one of the sides of the triangle ABE, that DF must divide the other two sides in the same ratio. So, we can say that BD by DA is equal to BF by FE. This is the second result. Now, from these two results, what is that? From the results 1 and 2, what can we say? Here both BE by EC and BF by FE are equal to same ratio BD by DA. That's why we can say that these two ratios must be equal. So, from the results 1 and 2, we can say that BE by EC is equal to BF by FE. Students, now let us do the fourth one in this exercise 8.1. That is, prove that a line drawn through the midpoint of one side of a triangle parallel to another side bisects the third side using B.P.T. First of all, let us picturize this situation. So for that, let us take one triangle and name it ABC. Now in this triangle ABC, let us mark the point D, which is midpoint of AB. Okay. Through this midpoint of one side AB, let us draw the line parallel to another side. Now through this midpoint D, let us draw the line parallel to the side BC. Then this parallel line intersects the third side AC at some point. Let us name it E. Now, by this question, we have to prove that this point E is the midpoint. Now, let us write the given conditions. the midpoint of one side. So here D is the midpoint. Given that D is the midpoint of AB. Therefore, AD is equal to DB. And the next one, the line is drawn parallel to another side, that is BC. So, what can you write? DE is parallel to BC. As it is given that DE is parallel to BC, by the basic proportionality theorem, if a line drawn parallel to one side, then that line divides other two sides in the same ratio. That's why as DE is parallel to BC, we can say that DE can divide these two sides in the same ratio. So by B.P.T, what can we write? AD by DB is equal to AE by EC. This is by basic proportionality theorem. But already we have got the condition that AD is equal to DB. It is given condition. So as AD and DB are equal, we can say that this fraction is equal to 1, is equal to AE by EC. And also here we have got that AE by EC is 1. That's why both numerator and denominator must be equal. So we can get that AE is equal to EC. As AE and EC are equal, we can say that E is the midpoint of AC. Therefore, E is the midpoint of AC. That we have proved. So bisects the third side. My dear children, shall we do the problem 6 in this exercise 8.1? Okay, let us see. In the given figure, DE is parallel to OQ and DF is parallel to OR. Show that EF is parallel to QR. First, let us take the given conditions. First condition is DE is parallel to OQ. This is the DE is parallel to OQ. Of course, this situation is in the triangle PQO. That's why let us write that in triangle PQO, what is given? DE is parallel to OQ. As this line is parallel to one of the sides, then by the basic proportionality theorem, it divides the other two sides in the same ratio. Let us write the same. By B.P.T, we can say that PE by EQ is equal to PD by DO. Take it as first result. Next, let us take the second condition. What is it? DF is parallel to OR. DF and OR. This situation is in the triangle POR. That's why in triangle POR, it is given that DF is parallel to OR. Again, the same situation what we have in the triangle PQO. Here also we have got the same. So, by B.P.T, basic proportionality theorem, here also we can say that as DF is parallel to OR, this DF must divide these two sides in the same ratio. That is PD by DO, PD by DO is equal to PF by FR. PF by FR. Take it as second result. From these two results, we can say that from 1 and 2, what can you write? As PE by EQ and PF by FR. These two ratios are equal to same ratio PD by DO. That's why these two ratios must be equal. So from 1 and 2 we can write that PE by EQ is equal to PF by FR. But here you see PE and EQ, PE and EQ and PF and FR. These two are the parts of the sides of triangle PQR. So here we can see that in triangle PQR, PQ by EQ is equal to PF by FR we have got. But these two equal ratios is obtained by the line EF, as EF is intersecting the sides PQ and QR in the same ratio we have got this. But by the converse of B.P.T, if any line divides two sides of the triangle in the same ratio, then that line is parallel to third side. So by converse of B.P.T, what can we say? In triangle PQR, EF is parallel to QR because EF is dividing these two sides PQ and PR in the same ratio. That's why here we can say that EF must be parallel to QR. This is the condition to be proved. Students, now let us do 8th one in this exercise 8.1. That is, ABCD is a trapezium in which AB is parallel to DC and its diagonals intersect each other at O. Show that AO by BO is equal to CO by OD. Now, to prove this result, first let us present the given information in the diagrammatic form. For that, let us first take the trapezium ABCD, in which AB is parallel to DC. That's why let us name these sides AB, CD. Here we can see DC is parallel to AB and its diagonals intersect each other at O. So the diagonals AC and BD are intersecting at this point. Let us name it O. We have to prove that AO by BO is equal to CO by DO. For this, let us take some construction. Here, let us draw a line parallel to AB or DC through the point O. Let us name this point of intersection as P. Now, after drawing this parallel line to AB or DC, let us consider the triangle BCD. Okay, before that, let us write the construction. Draw a line parallel to AB through the point O. Let it intersect BC at the point P. Now let us consider the triangle BCD. In triangle BCD, here what can you see? OP is parallel to DC, because if OP is parallel to AB, it is also parallel to DC, because AB and DC are parallel sides in the trapezium ABCD. That's why here we can say that OP is parallel to DC. As this line is parallel to one of the sides of triangle BCD, by the basic proportionality theorem, we can say that this line divides other two sides in the same ratio. So, what can you say? By B.P.T, basic proportionality theorem, we can say that BO by OD is equal to BP by PC. Let us take this result as first one. After getting this result, let us take the triangle ABC. In this triangle ABC also, we can see that OP is parallel to AB. OP is parallel to AB. Again, by the basic proportionality theorem, here also we can say that as OP is parallel to AB, this line must divide the other two sides in the same ratio. That's why here we can say that AO by OC is equal to AO by OC is equal to BP by PC. BP by PC. Let it be second result. Now from these two results we can see that AO by OC and BO by OD are equal to same ratio BP by PC. So let us write from 1 and 2. What can you write? BO by OD is equal to AO by OC. From this result, BO by OD is equal to AO by OC. With the help of alternando property for the ratios, we can get the result that OC by OD is equal to AO by OB. That is, AO by BO is equal to CO by DO, which is the required result. Okay children, in this class, we have discussed some definitions related to similar triangles and some problems in exercise 8.1. In the next class, let us discuss some more important points and related problems in other exercises also. Thank you children.